All right. Okay, thanks. So Andras is going to tell us about the instrument team disk observing programs with JWST. All yours, sir.
All right, thank you. Can everyone hear me? Yes. Well, all right, thank you. There's a lot of us here. That's fantastic. All right. First of all, let me thank the organizers for giving me a chance to talk to you today. We have a lot of great talks and a lot of great posters at this meeting. My name is Andras Gaspar. I work at the University of Arizona. I'm an associate research professor there, and obviously my slides are going forward. And I've been a member of the JWST, MIRI, and NIRCam GTO teams for a very, very long time now. Today I'm going to talk to you about the JWST, GTO, NIRCam, and MIRI debris disk surveys. And since Christine gave an amazing review talk of debris disks, I'm going to skip the whole spiel about why debris disks are important, get straight to the point. So we executed 2 large debris disk surveys with JWST in cycle 1 and 2. This is the GTO 2780 scatter light disk program that I co-led with Jaren Leisenring. This is an over 50-hour survey on the 5 most prominent and brightest debris disks that we could observe at JWST at scatter light. And the GTO 1193 MIRI archetypical disk survey, which looked at the 3 most prominent disks where we could hopefully detect their asteroid belt analog regions. As I said, these are GTO programs, so we started planning these programs long before the launch happened, so about 2017 or so. I'm going to get straight to the results. So the NIRCam scatter light disk program observed these 5 targets. 10647, 32297, and so on. I'm sure all of you are well aware and familiar with the HST images of these systems. They're beautiful. They're located around various spectral type sources. The disks themselves are located at spatially, physically different regions, but they're all spatially very well resolved with HST. The systems themselves are various in age, so we wanted to make sure that we cover a large range of physical properties of systems. So these are the HST images, and I'm going to show you how the NIRCam images of these systems look like now. This is what we see with JWST. All the disks are beautifully spatially resolved with NIRCam. We observed all systems with 6 filters altogether. 2 of the systems we also observed with MIRI. Today, due to lack of time, I'm only going to talk to you about results on one of the systems, and I'm also going to talk about lessons learned and the way to post-process and observe systems with both instruments. So today I'm going to talk to you about Q1 ARI, only the system that Carl is very interested in for Roman. So these are our 6 NIRCam images of the system. As I said, they're all really spatially beautifully well resolved at all 6 filters, going all the way from 1.8 microns all the way to 4.4 microns. And this was one of the systems where we even have a MIRI imaging. As you can see, it actually has a bright extended inner core, so there's an inner disk, warning to Carl. What can we do with these observations? Well, as Christine said, with these types of observations, we can already start looking at scattering phase functions. So, for example, here is the scattering phase angle region for the system. Goes all the way from 13 to 167 degrees. So with its inclination, this system gives a really wide range of scattering angles that we can study. And if you can compare it to Saturn's rings from Heitman and Stark's paper, you can see that the scattering phase function agrees really well with what we see, for example, for the dust particles around Saturn. So really neat. What else can we look at? Well, with the 6 filters, we can do broadband spectrophotometry and compare it to other observations. For example, here we're comparing this system to that of C67, 238 read, and the TNO objects that JWST also observed. And what we see is that the spectra are more similar to inner solar system objects than they are to outer Kuiper belt-like objects. So really neat. This would be an ideal target, I think, for near-spec follow-up. And we see water dip at 3 microns. So there's water ice in the system, and so on. All right, I wanted to talk a little bit about image processing, since this is more of a technical conference, I think. So for all of our observations, we had 2 rotations and the 5-point small grid dither pattern, which is classic for NIRCam observations. And as most people, I tried to do something a little bit different or improve on methods. And what we tried to do here is perform a hybrid classic and locally, or not locally, but linear combination PSF image processing. Since these are extended sources, if you do an automated algorithm, your processing will over-subtract the inner core, which is not really ideal. And a way out of that is doing classical RDI, where you just scale each PSF to the observed source, median combined, but that will result in speckles in the contrast-dominated region. But this would help in the outer region where you're photon-dominated, right? So how can we combine these two? We thought of a way of doing this by putting in an extra constraint, which is that the coefficients should add up to the scaling between the star and the PSF ratio. This adds an extra constraint, so the coefficients are not independent from each other, so we need to do a numerical solution to this problem, but we can set it up in a way where the coefficients actually meet to the same value at the end of the edge of the field. Therefore, we combine the best of both worlds. We have a really good image subtraction in the center of the image, and we have really high signal to noise by the edge of the field. So this is what we get. If you do a classic RDI, you get pretty nasty inner core subtraction. If you do a linear combination RDI, you get much nicer center part. But if you do the hybrid method, where you can constrain the total scaling of the combined PSF, because you know that from physical aspects of the system, you can get a really nice final subtraction. All right, with that, I'm going to move on to our MIRI program, the 1193 archetypical disk survey. I really love this program. We looked at Fomalhaut, Vega, and Epsilon Eridani, the three systems ideal in terms of spatial distance and spatial resolution, where we could possibly image the inner asteroid belt analog components. These are three systems where we could do this best, and we wanted to see where are the asteroid belt analog regions located in these systems. Are they narrow, like we have in our solar system that we assumed that we would see? And could we see any structures in them, possibly indicating presence of planets? So these are the images of the systems pre-JWST, and I'm sure all of you have now seen our JWST images of these systems. They're beautiful. What do we see? Well, for all three systems, we see an extended inner region, meaning they're not at all like our solar system, right? And our solar system is a very narrow asteroid belt. Here we have an extended inner belt. We also see structures. Fomalhaut has this intermediate ring. We've got that gap there. Vega has a dip in it. So we can see structures in these inner regions. So what did we learn? One, we have an extended inner region in all of these systems, indicative of dust transport happening. And we're going to talk about that a little bit. And we see structures. So possibly we can talk about planets in these systems. All right, so here are some simulations, one for each of the three systems, where we invoke the particle transport, both from Poynting-Robertson drag and stellar wind drag happening in all three systems. I chucked in a planet in all three systems, so for Fomalhaut, we put one at 78 AU, a very low 0.6 Saturn mass planet. For Vega, put in a 1 Earth mass planet at 60 AU, and for Epseri, we put in Epseri B. And what do you see? Particles being dragged in for Fomalhaut, Vega, and Epseri. You see the inner structures being produced. You can see the perturbations. The contrast was a little bit better. And Fomalhaut, you see an inner belt being produced. You see the dip at Vega. If I put in even a 6 Earth mass planet for Vega, that dip would be completely destroyed. So we can constrain the mass of planets in the Vega system just from the images. And for Epseri, you see actual structures in the disk with Epseri B put in. So there's a question whether something's going on in there. So how does dust transport work? Well, first of all, let's compare these to actual observations. They match up quite well. That's the good news. So how does dust transport work? I'm going to break the first rule of presentations. I'm going to show you an equation here. This is simply the equation of motion for dust particles. Obviously, we have gravity. We don't care about that. Radial pressure, it's determined actually both by radiation pressure and stellar wind pressure, also pushing particles out. But the beta of stellar wind is always much smaller than beta of radiation. So it's not important when it comes to pushing particles out. But what about drag term? If you look at the drag term, the beta of drag is actually divided by the speed of light, while the beta of stellar wind is divided by the velocity of the stellar wind. So if beta SW is large, which will be large if you have lots of mass being thrown off by the star, then that can become important. And that's why for later spectral type stars like Epseri, it becomes important. So we have both radiation from Poynting-Robertson drag and stellar wind bringing in particles in these systems. All right, what did we learn about high contrast direct imaging with MIRI? How do you take the best observations for MIRI for direct high contrast imaging with MIRI? Image dithering is absolutely necessary. I don't know why that skipped out. Let's go back here. So do take dithered images. Background observations are nice, not necessary. Rotational dither, nice to have, not necessary at all. However, position and brightness matched PSF are absolutely critical. If you're going to be taking MIRI, direct, high contrast imaging observations, please get a position matched PSF. Why? Let me show you an example. These are two PSF observations at 21 microns for two different stars. So here are the 4 points, position 1, 2, 3, 4, taken at two different epochs, two different brightness stars. Let's subtract all different combinations of the PSF. So P2 from P1, P3 from P1, P4 from P1, and so on at the two different epochs. This is what we get. This is a subtraction matrix. Horrific images, right? Lots of PSF residuals. Why is that? The PSF is position dependent across the MIRI detector. Again, same PSF, same time, within 20 minutes or so, same brightness, same OPD, same brighter, fatter effect, yet we get horrific subtractions. But what happens if we subtract position-matched PSFs from the two epochs from each other? And note, these are different brightness sources. Well, then this is what you get. Beautifully subtracted PSFs. Why? Because you're subtracting the PSF taken at the same position. So please plan your observations this way. Again, different PSF, different time, different brightness, different OPD. They'll have different brighter, fatter effect. That's why you have those little residuals. But if you even imagine a brightness, even those will be subtracted. So comparison. Finally, we can center MIRI PSFs extremely well, within 0.01 pixel accuracy. That's how great the MIRI PSF is. All right, and with that, the key takeaways for my talk. 1, NIRCam debris disks are showing potentials. Lots of similarities with icy comets in the solar system. NIRCam chronography, we tried different types of post-processing methods, seems to show promise. MIRI debris disk observations, we can see particle transport being dominant for lots of systems, so beware HAB worlds and GMAG AOX. We're going to see a lot of dust in the inner regions of systems, especially ones with outer belts. And MIRI direct high contrast imaging, please take position matched PSFs, and I'd actually like to advocate for the community to sort of agree on positions and always take our observations at those same exact positions so we build up a library of good PSFs at the same positions. All right, obviously this takes a huge village, so I'd like to thank everyone that worked with me on all of these programs. And with that, questions?
Okay, thank you, Andras. Do we have questions? Whoever's got the mic. Elizabeth.
Yeah, to your point about position-matched PSFs, how precise does that need to be? Like, do we need sub-pixel matching with target acquisition, or just kind of roughly the right quadrant of the detector?
So these were quite extended patterns. That's why it was so bad. If the PSFs are closer to each other, they'll match better, but then you can't generate a background image easily. So it's a trade-off.
Okay, do we have one on this side? Can we get a mic to Chris also? No, go ahead.
So similar question going in a similar direction. So in terms of calibration, couldn't you just like go and take PSF images on the entire detector once and then learn the function of X, Y position to shape all the PSF and then...
Talk with Marshall. Yeah, but even then, you will still need to interpolate and simulate. It's empirical PSFs always work better. Sorry.
All good. Continuing the theme of position-dependent PSFs, is this more of a field-dependent distortion effect, or is it detector systematics, or something else?
It's the waveform error of the telescope. It just there. He said the waveform error of MIRI itself, the instrument, varies across.
Copy that. Thank you.
All right, enough about PSFs.
I'm glad it made an impact.
Can we talk about epsilon Eridani B?
Yes.
And can you elaborate on the tension? And yes, when I saw your image, I freaked out.
Oh, don't freak out. So Skylar would be able to give you all the details. She's the one who modeled it. The disk itself, if you look at the observations, there's a PSF artifact residual, and you can model where an inner ring would need to be to produce those PSF artifacts. For FOMOD and Vega, we had really clean subtractions, not for EPSARI. And it would produce a ring within the inner regions of the system that could still be okay with EPSARI B's orbit, but barely, right? Skylar, you're around? Yeah. She said that's right, okay.
Last question.
Thanks. So you modeled the inner disks as migrating dust inward from the outer disks. Makes total sense, right? But how do you tell the difference between that and dust being blown out of an inner disk?
Aha. Well, I assume we would need to go and get scatter light images, which we have for Vega, so we could potentially go and look at that. But the transport model works.
Okay, that's all we have time for, so let's thank Andras again.